One really interesting insight is that deep networks can learn random labels. So these authors performed an experiment where they would assign random class labels to images. And they ask, can the network learn these random class labels? So what is the generalization error of random class labels? I mean, we would expect that if we use random class labels during training and we have a test set with random class labels or even real class labels, that we will not be able to learn much. So we would expect that what we train on will not help us to get good results on the test set. So just to clarify, on top we see 4 images that depict 4 objects. First image is a dog, second a banana, third a dog, fourth a tree. But what we're going to do is we'll just roll some dice, so we pick a random number and assign a new class label. So maybe the first one is a banana, the next one is a dog, then we have a tree, and then maybe we have a dog again. So what we see here is that this is the performance on the training set in blue, and this is the performance on the test set. So the idea is that on a training set, you can get very high accuracy. In this case, it's always 100%. And on the test set, so this would be for the regular training set, you can get something that's a bit worse. So that's kind of the reasonable baseline that's shown here, where no randomization has been applied. Now what we're going to do is we'll replace more and more of the labels during training with random labels. And then we can see that the network still has the expressive power to fit any type of labels. So the training set accuracy stays at 100%, even in the extreme case of complete randomization, the whole training set is randomized. But as expected, the test set performance drops continuously until at the end the test set performance should be completely random. So why is there 100% accuracy on the training set? Well, as we see in the paper, it is indeed possible to get 100% accuracy on the training set if one trains with a small enough network, so a small enough data set that is CIFAR 10, and one uses big enough networks such as inception and inception without batch norm, or what is this, MLP. And what we see in this column, training accuracy, is that consistently this 100% accuracy can be achieved, at least for certain networks. Maybe AlexNet can not achieve it in all configurations. And one idea is that this depends a bit on the regularization used, but even what we see here is even with regularization such as weight decay, a training set accuracy of 100% can be achieved. Also, using random labels, what we see in this row, we can achieve a training accuracy of 100% without regularizers. Maybe looking at AlexNet, fitting random labels here, we do not get the 100% precisely, but it's pretty close. So this paper is something very different. It's a training strategy to improve the accuracy on ImageNet. So the idea is to have some version of a teacher and a student network. So the concept of a teacher and a student network is that we could have a teacher network that is maybe trained on some task, let's say ImageNet classification, and this teacher network will predict probabilities that for each of the images. And so a student network could now be trained to not learn class labels, but a student network could be trained to emulate whatever a teacher network predicts. So this is just to establish these two terms, teacher network and student network. So we will see concepts of teacher and student network in this paper as well. The other concept that is used here is, what if we have not only ImageNet with labels, but what if we have another much larger data set of maybe a few 100 million images that is unlabeled, but that we would like to use to somehow improve the ImageNet performance. So let's look at the final result. What we see in this figure is the previous state of the art using EfficientNet in blue, and then using this noisy student training idea is giving us the red curve. So since it's higher accuracy and it's better. And the improvement in ImageNet top 1 accuracy is quite significant. It's about 1%. The reason why 1% is significant is because this is such a competitive task with so many highly fine-tuned networks that it is not easy to get 1% more. 1% on some other tasks that are much less competitive might not be a significant step forward, but on something like ImageNet, 1% is really a significant improvement. So we'll introduce this term pseudolabel here, and this is a label assigned by a trained network. So assigned by a teacher network. Then there's a difference between hard and soft labels. So a hard label is 1 for the correct class and 0 for the other classes. And soft labels are softmax probabilities. So this is the output of a network that is used to label the result. So if someone is training to achieve soft labels computed by another network, then the new student network being trained will more directly emulate what the teacher network is actually computing. The main ideas are self-training and add many sources of variation noise to the student. That's also where the paper or title comes from. And no noise in the teacher when generating pseudo-labels. The surprising thing here is that probably many similar variations of this have been tried, and the authors here found one variation of well-established concepts that seems to work really well. So when we talk about sources of noise, what are we actually talking about? For example, dropout, stochastic depth, data augmentation are sources of stochastic noise, are sources of noise. And so the idea is that one training can be used with noise and the other training can be done without noise. Some minor detail is this idea of data balancing for pseudo-labels. So when one trained network assigns pseudo-labels on the dataset, then we're going to duplicate images in classes with not enough images and take highest confidence images for classes with too many images. So some classes not enough images, so we duplicate. Others, there are too many, so we take the highest confidence ones. Alright, it's maybe a bit cryptic, so let's just look at the algorithm to make all of this clear. We have a set of labeled images, and this set of labeled images is pretty large. So let's say this is ImageNet, and then we have another set of unlabeled images, and this is even larger, let's say a few 100 million images, something that Google and Facebook has. So first, we're going to learn the teacher model theta star, which means let's just say we are taking ImageNet and we're taking the EfficientNet architecture. That means we're learning the parameters of EfficientNet of a teacher model by training on ImageNet using established ideas such as cross-entropy loss, and we are using the labeled images from ImageNet. And the teacher model is being trained using this fnoise, which means it uses the source of noise, such as dropout or data augmentation, as discussed on the previous slide. Then we go to this very large data set, x1 tilde to xm tilde, and we use this trained teacher model, but without noise, to predict the pseudo-labels on this very large unlabeled data set. So we predict these pseudo-labels yi tilde for each unlabeled input image xi tilde using the teacher model theta star trained in step 1. And we do this for all the images in the dataset of unlabeled images. It's possible to do that with soft or hard pseudo-labels. Third, we're going to learn a student model, theta star prime, and we're going to train this on the original labeled dataset ImageNet and also on this other very large dataset. But for this very large dataset, we now use the pseudo-labels that were generated in step 2. Now notice that as we are training this student model, again we use the sources of noise, such as dropout or data augmentation. And we do that for both the initially labeled images and the unlabeled images that now have pseudo-labels. Finally, we have iterative training. Now we have a student model that becomes the teacher model, and we go back to step 2. This now trained student model, that is the new teacher model, can again predict soft or hard pseudo-labels on the dataset of unlabeled images. So we get refined unlabeled images, and then we can iterate. We're going to train again a student model, then it becomes the teacher model, predicts hard or soft pseudo-labels, and then again there will be a student model trying to emulate the soft and hard pseudo-labels. But the trick again is always that for the prediction in step 2, the noise is not used, and for the training, learning in step 3, the noise is being used. So another question about generalization asked by the group of Recht is, do ImageNet classifiers generalize to ImageNet? So maybe another way to discuss this paper would be to ask the questions, are more recent networks better, or do they just overfit the training data? Actually, this should say training and test data. So what is the effect of using the same test data over and over again? So the idea is maybe because there are so many tests being done with the same test data that somehow the networks would overfit, and that actually no real progress would be made. So this is one of the dangers of using the same test set over and over again, of using the same data set over and over again. So the authors propose the following test. They create a new test set for CIFAR 10 and for ImageNet. They try to follow the original protocol for dataset creation as closely as possible, and then they evaluate networks trained on CIFAR 10 and ImageNet on the new test sets. And this is done without doing any extra new training. The authors just go on the internet, download existing networks and their weights, and then they test these downloaded networks on their new test set. I found this was a really exciting type of question to ask and a really exciting test to perform. So what's going to happen? Are we going to see that newer networks actually do the same as older networks? Will the gap kind of be closing? We see some evidence of strong overfitting on the test set. Let's look at the main results shown in the paper. On the left, we see the results for CIFAR 10, and on the right, we see the results for the much larger dataset ImageNet. Each model is a data point, such as this model here, and the model has two accuracies. One is on the original test set, and the other one is on the new test set. So this model that we circled here has an accuracy of about, let's guess, 88 on the original test set and maybe 78 on the new test set. So this particular model has a lower accuracy on the new test set, and quite significantly so, maybe like 10% lower accuracy on the new test set. This black dashed line here, this shows the line where the test set, where the accuracies on both test sets would be the same. So since all the models are below this line, we can say that all of the models, they have much worse performance, since they are far below the line, on the new test set than they have on the original test set. There are many different architectures proposed for ImageNet, and each of them is this dot, and then these bars are some sort of statistical certainty that we are not going to go into. What we also have is a red line that illustrates some linear fit. What we can observe also using this trend line through the linear fit is that architectures that have better performance on the original test set, either for ImageNet or CIFAR, they have better performance on the new test set. So the performance on the original test set is a predictor for the performance on the new test set. That means that the performance on the original test set still tells us a lot, and in some sense we could say it preserves the ordering between the quality of the architectures. What is stronger visible for CIFAR is that the gap between the new test set and the original test set is closing fairly quickly. For ImageNet, we observe something that's almost more like a constant offset. Seems like for ImageNet, everything gets 10% worse when going from the original test set to the new test set. So the second thing is the explanation for these crosses. These are the 95% Klopper-Pearson confidence intervals. So there are two main conclusions. First, there's a significant drop in accuracy from the original test set to the new test set. And second, as discussed, the model accuracy closely follow a linear function with a slope greater than 1. Again, that means that each percentage point of progress on the original test set translates it to more than 1 percentage point on the new test set. The authors propose the following analysis. So there could be 3 possible reasons to explain these experiments. One is a generalization gap. The test set is sampled from this assumed population of images, and it's just some random sampling of that, and this possible huge infinite population of images, we're just going to sample a test set, and sometimes we're going to sample a harder one, and sometimes we're going to sample an easier one. So maybe we just, with the new test set, randomly sampled a harder one. The authors argue this is not likely to be the reason because the difference in performance is simply too large. So if the test set only has 5 images and you sample randomly 5 images, there's a high chance that one time you sample 5 easy ones and another time you sample 5 hard ones. At least very plausible. But if you sample 100,000, then it's difficult to kind of think that, okay, once you sampled significantly harder samples in such a large quantity, this cannot really be explained by random sampling. Second is the distribution gap. The new data has harder samples, possibly due to systematic differences. We could think that maybe the camera changes over time. Maybe in the original ImageNet dataset, there were lots of cell phone images from one particular time, and now the cell phones are very different, and now the images have some differences that maybe are subtle for a human, but the network really picks up. Or maybe the protocol of following this protocol of generating the dataset, maybe the new interpretation was a bit different, or maybe back then people were a bit more sloppy, or in the new dataset people were a bit more sloppy. So any sort of differences like that, or maybe there hasn't been the interpretation of the protocol was different. So any systematic difference could be used to explain this large gap. And the authors conjecture that this is really the main reason to explain the difference. And the last one, and this is the really interesting question that is asked here, is the adaptivity gap to blame? And what is the adaptivity gap? That is maybe that these networks are, for subtle or not so subtle reasons, adapted to the test set. It's a competitive world out there, and we all know it's forbidden, but rather than getting fired, maybe some of these people started to train on the test set, or maybe they mix a few images from the test set into the training set, something that would be really, really illegal. But it doesn't have to be like outright that bad. Maybe people do something more subtle, like tuning hyperparameters on the test set, or maybe even less subtle. Just these architecture choices get made and then evaluated ultimately on the test set. And then these architecture choices, maybe over time, they are more and more informed about the test set. And then, in some sense, the information in the test set leaks more and more into this architecture design. So this is a general concern and a big concern for any type of data set, that over time people try to strongly overfit, or will tend to strongly overfit on a data set. So the real significant insight that the authors propose here is that they say, actually, this overfitting to the test set is not something that they observe. And this goes back to this analysis before, where you saw that being a bit better on the test set or original test set of ImageNet gives you more payoff even on the new test set. That means that there is really no sign of this overfitting happening. And in research or machine learning in general, of course, it's a competition. So people compete on these data sets, and then one person will win, and they will say that, of course, they won because they're the best, but everybody who lost, they tend to say that, of course, they lost because they didn't have as many GPUs to train on, or, and you hear that a lot, that is because the other person just overfit on the test set. So this is a very strong belief that for a lot of these networks, that they would just overfit on the data. Of course, this happens, but here we see one example of an analysis that actually concludes that this overfitting doesn't seem to be nearly as bad as people always claim it is. All right, this concludes this lecture on network analysis. I would like to say that these are some of my favorite papers. I really liked all of these papers that I presented in this lecture. And I would like to also add, again, this general warning. A lot of this is experimental research, so you always need to be careful how much faith you really put into this analysis. If you want to know more, go read the original papers. But at the same time, don't be surprised if then a few years later, people come up with some other analysis that maybe points in a slightly different direction.